In this video, I will briefly discuss about chapter 6, which is the system of first order linear equations or linear differential equations. Okay, so in chapter 3, what you saw is if there are a pair of linear differential equations, okay, how do we solve them? Okay, so what we did is we write that in the matrix form and we find out the eigenvalues of the matrix, okay, and then find the eigenvectors. And what we did is we write the solution is equals to e to the lambda 1 t and then vector of the eigenvector of the for the eigenvalue lambda 1 and plus c2 times e to the lambda. So all those methods, okay. So the same techniques will be used if there are more than two differential equations, okay. So how do you write that in the matrix form? Exactly the same technique, same method, okay. So if there is like n differential equations, you see that. So x1 prime equals to p11 x1 plus p12 x2 plus and then plus p1 and xn plus g1. This is the non-homogeneous term on the right side, okay. And x2 prime is p21 x1, p22 x2, and so on. And then there are so many, and then xn prime, the last one, is equals to and pn1 x1, pn2 x2, and then pn1 x1 plus xn plus gnt, okay, where all these p11 p12 are a function of t, and then xi are a function of x1 x2 x3 are also function of t, okay. So this whole system can be written as xt prime, this is vector x, where vector x is x1 x2 x3 x4 x5 like that, equals to pt. What is p? P is p11 p12 p1n and p21 p22 and then dot p2n and then so on, right? So this is also another matrix, okay. This is a matrix, this is another matrix, and times xt is that matrix here, x1 x2 x3 x4 like that, right? So x1 there is prime outside, x2 and then dot and then xn, right? And this is p11 p12 and then p1n and p21 p22 and then so on, right? And last one is pn1 pn2 and so on. And G, the matrix G is, this is also x1 x2 x3 and so on, and plus G will be g1 g2 g3 g4 g5 like that, okay. And this is the initial condition. So this is how we write the system of ordinary differential equations. Now also recall from chapter 3 that if you have a second order differential equation, y double prime plus 5y prime plus 6y equals to 0, you can write this as a system of two ordinary differential equations, right? So that is x1, we said x1 equals to y and x2 equals to y prime. Then x1 prime equals to y prime and x2 prime is just differentiate on both sides. You give you y double prime, that is equals to minus 5y, because when you solve this for y double prime, you'll get minus 5y minus 5y prime minus 6y. That can be written as, because this is basically x2 and this is basically x1, right? So you can write minus 5x2 minus 6x1, and you can write this as a matrix form, right? You can write x1 x2 prime equals to, you can write 0 1 and then minus 5 minus 6, you can write, and then x1 x2, right, this way, right? So this is a homogeneous system, you see that, and then you can solve this system by using the eigenvalue method, okay. So, but if this is a non-homogeneous, we use different techniques to do that, right? We did the particular solution and the complementary solution, right? So we did that way. But if it is a homogeneous, then you can do the eigenvalue method. Okay, let us see the existence and uniqueness theorem for the system of ordinary differential equation. So what it says is, if pt and gt, look at this system, okay? We are talking about this system. If pt and gt in the equation star are continuous in an open interval I, then there exists a unique solution x equals to phi t of the initial value problem, this, where t0 is any point in the interval I. Moreover, the solution exists throughout the interval I, not only at a point, but the solution exists anywhere in that interval, throughout the interval I. That is the existence and uniqueness of the solution. Before we go to any examples, let us see some terminology we use here, the one thing you have seen in the linear algebra is the non-defective matrix. Okay, a square matrix A, which is a size n or n by n, is called defective if it does not have a linearly independent n linearly independent vectors. Okay, if a matrix has size n and if it doesn't have n linearly independent eigenvectors, then it is called defective matrix. So let us see a theorem. Let lambda 1 v1, lambda 2 v2 up through lambda n vn be eigen pairs for n by n constant matrix. Assume that the eigenvalues are real and the corresponding eigenvectors are linearly independent. If all the eigenvalues are real and all the eigenvectors are linearly independent, meaning that this is a non-defective matrix, okay, then this set e to the lambda 1t v1, e to the lambda 2t v2 through e to the lambda nt v, and this set makes a fundamental set of solution. So what is the general solution is you just add them, take the linear combination of those, right? So lambda e c1 e to the lambda 1t v1 plus c2 e to the lambda 2t v2 plus, and then go through cn e to the lambda nt vn, where c1 and c2 are the arbitrary constant. Okay, so we'll see some of the cases of the 3x3 matrix, 3 differential equations. Okay, if there are 3 distinct eigenvalues, so it will have 3 linearly independent eigenvectors. So in that case, the solution will be exactly same as that. The next case you will see is 1 real and 2 complex eigenvalues. Okay, so real is lambda 1 and complex are lambda 2, 3. They will be conjugate. So alpha plus minus beta I. Okay, eigenvectors will be v1 plus v1 and v2, and v3 will be just the conjugate of v2, right? So that's what the eigenvectors look like. So in that case, the solution will be x equals to c1 e to the lambda 1t v1 plus c2 u plus c3 w, where e to the lambda 2 v2, lambda 2t v2 and e to the lambda 3t v2 v3, exactly same as what we did in the 2x2 matrix for this part, for the second and third. Okay, we simplify that to that one, okay, because lambda 2 and lambda 3 are alpha plus minus beta I. You simplify that, and for this I beta t v2, e to the I beta t v2, we use the Euler's formula, okay, and simplify it to get the form of u and w, and then you write c2u plus c3 w for the second and third. The first one remains the same. Okay, the third case is 1 real and distinct eigenvalue and 2 real and repeated eigenvalues, because there are three equations, right? 3 differential equations. In that case, if you get 1 real and distinct and the 2 of them are real but repeated eigenvalues with only one eigenvector, if there is only one eigenvector, then the solution will look like this: c1 e to the lambda 1t v2 plus t times e to the lambda 2t xi zeta plus e to the lambda 2t rho, where a minus lambda 2 I xi equals to 0. So this xi is calculated as like a eigenvector, the regular eigenvector. Okay, for the rho though, what you do is you must satisfy a minus lambda 2 I rho equals to xi. You do that and then you find out the rho. Okay, we did this in the 2x2 matrix case, 2x2 system case also. Okay, and the number 4 case is 1 distinct and 2 repeated eigenvalues with 2 independent eigenvectors. So you will have one eigenvector from the one eigenvalue, and then 2 of them are repeated eigenvalues, but the eigenvector are also independent. Here there is only one eigenvector, but here is 2 independent eigenvectors. In that case, it is just the normal case. So you do the general solution will be xt equals c1 e to the lambda 1t v2 plus c2 e to the lambda 2 v2 plus c3 e to the lambda 2t v3. That's what you do. Okay, so the next cases are case number 5 is 1 triple eigenvalue with 1 eigenvector. If all the eigenvalues are repeated and there is only one eigenvector, then how do we handle that? Okay, so the other couple more rules are: if the eigenvalues are repeated with only one eigenvector, if all 3 eigenvalues are repeated but there is only one eigenvector, then it will look like, the solution will look like this: xt, the general solution, is equals to c1, so t square e to the lambda t xi plus c2 t times e to the lambda t rho, and then c3 e to the lambda t times zeta. Okay, where xi and zeta are given like this. Next one is a repeated eigenvalue with 2 linearly independent eigenvectors. So in that case, if there are two linearly independent eigenvectors, only the one is repeated, right? Eigenvalue with it has eigen vector, but there are just two linearly independent eigenvectors. In that case, what you do is you do e to the lambda t. So all the eigenvalues are the same, but only there are only two eigenvectors, two linearly independent eigenvectors. So what you do, c1 e to the lambda t v1 plus c2 e to the lambda t v2, okay, and then plus c3 times t e to the lambda t zeta, okay, and then c4 e to the lambda t rho. That's what you write, okay. So actually what you can do is you can basically see that the one that is because since all the eigenvalues are repeated, you will have, and but there are, if there is only one eigenvector, then this way you will get t square and then t and then on. But if there are two linearly independent eigenvectors, then you will have t times, okay, one of those will be t times, but you can combine those vectors at the end to the two vectors, okay. So where z and xi are given, z and rho are given, xi and rho are given by that. So the next one is the repeated eigenvalue in three linearly independent eigenvectors. If the eigenvalues are the same but the eigenvectors are three different linearly independent eigenvectors, then in that case you will have as number 1, okay, c1 e to the lambda t v1, c2 e to the lambda t v2. So lambda t will be the same, but v1, v2, v3 are the different. So you can extend this rule for the 4x4 system as we had in the, as we extended from 2x2 to 3x3, okay. So let us see one example that doesn't have the system, but it has a third order derivative there, okay. So you have y triple prime plus minus 5y double prime minus 22y prime plus 56y equals to. So we did this type of example too, right? What we did is we find out the eigenvalue first. How? This is lambda to the third minus 5 lambda square plus 22 lambda plus 56. So find out the characteristic equation like that, and you solve that for lambda. I use the synthetic division to find out the lambda. So I plug in 1, it didn't work. So when I plug in 2, I get remainder is 0. So 2 is one of the solutions. So I use that 2 to find out the. So I use that 2 to find out the quotient, right? And when I did that, I got all the real and distinct eigenvalues are 7, 2, and -4. Real and distinct. So the general solution will have this form, right? And we use the initial condition to get this final form. So basically, this is not hard at all. Okay, so this is just the extension. So so this is the end of this course.